So we have already discussed up to the fringe width calculation of the interferences, and now we will discuss certain things based on that. First of all, the fringe width that we discuss is beta, that is equal to lambda capital D by small d, and distance of the nth order right fringe that we found xn equal to n lambda d by d. Okay. Now write down one problem. In a Young's double slit experimental setup, for a light of wavelength lambda 1, and for another light of wavelength lambda 2, eight bright fringes and 12 bright fringes, 8th bright fringe and 12th bright fringe are found to overlap. Okay, what is the ratio of wavelength of the two lights? What is the ratio of wavelengths of the two lights? For lambda 1, 8 bright fringe, and for lambda 2, 12 bright fringe overlaps. Then what is the ratio of lambda 1 and lambda 2? That you have to find. For first one, it is x8. That will be equal to n1, suppose. n1 is in a 8. So you can directly put in here 8. Lambda 1 capital D by small d. For second one, it is x10. It will be 10 lambda 2 capital D by small d. These two overlap means x8 equal to x10.
x12, sir. x12. 12.
Oh, this one is 12. Okay. These two will overlap, means these two will be identical. So just put 8 lambda 1 d by small d will be equal to 12 lambda 2 d by small d. So d small d will cancel. So you can write lambda 1 by lambda 2 equal to 3 by 2. So the ratio will be 3. Okay. Then next one is, suppose in Young's double slit experiment, instead of monochromatic source of light, a white point source of light is used. Then what will be the change in the interference pattern formed on the screen. Suppose previously we used yellow, a monochromatic light. We got bright fringes, all bright fringes are yellow, and dark fringes means dark. Now we use a white light. Then what will be the change in the interference fringe pattern? What is the change in interference pattern, fringe pattern, if instead of a monochromatic light we use white light?
The different colors scattered and the least scattered is.
We are discussing interference, not the scattering.
No change. No change.
No change. Okay, fine. I will ask you about one experiment. That is the Young's double slit experimental setup. In any path of the light wave coming from either S1 or S2, that diagram is already drawn in your copy. Just open that diagram of Young's double slit experiment. I will draw a proof diagram. Just this one, not the entire. And suppose in the path of this ray, I introduce a glass slab like this, of thickness T, and refractive index of this slab is mu. Outside medium is air. These are the two waves coming from S1, S2, and central line. This is the screen where they meet, and they are produced by two slits, small openings. Behind this there is a point source. Yes. All the things that we have discussed. This one. This diagram we have already discussed. S1 and S2 are the two secondary sources derived, and that is the point P, and at point P the light ray will meet, and as a result we know that path difference is S2P minus S1P, that we have already calculated. If that distance is x, we have calculated that this one will be x small d by capital. We have already calculated this one. This is the path difference, and according to path difference there will be a phase difference of 2 pi by lambda into path difference. Now in the entire setup remains same, only I take a glass slab, rectangular glass slab, and put it here in the path of the first light wave. Is and we consider initially monochromatic light, that is say yellow color or red, anything but monochromatic. And in the path of the wave 1 we put a rectangular glass slab in such a way that light wave is going perpendicular to this surface of this slab. Okay. Now what is the change in the fringe pattern? Is there any change in the fringe pattern? Because what we have to measure the thickness of the slab. Thickness thickness of the slab, that T I have to measure. Don't say that I have a scale and put it over the slab and I can measure the thickness. By interference experiment, we have to measure the thickness of the glass slab. Then, if you have to measure it on the basis of the interference experiment, then once we put the glass slab in the path of any one of the wave, then there is some change in the fringe pattern. So what is the change in the fringe pattern? Because that change I have to measure, and from that I can measure the thickness of the slab. So what is the change in the fringe pattern?
Fringe width will increase. The fringe width will increase.
Fringe width will increase. Okay. How much? Or the entire fringe system is shifted. Because path difference of every point will change. Because the optical path will change. Because inside the glass light travels slowly. So optical path will change. So there is a change in the path difference, implies that there is a change in phase difference. And as soon as this phase difference changes due to the introduction of the slab, the entire fringe system will be shifted because path difference for every point will change. Now, what is the previous position of the central bright? Here. Huh? Because both the light rays coming to the central bright are traveling same distance. Light waves coming to the central bright traveling same distance, so they have no phase difference. They have no path difference, they have no phase difference. Because S1O and S2O, these two lengths are same. But if you put this slab in the path of this central bright, then light goes slowly inside the glass, so there is a path, optical path for the wave 1 will change. Geometrical path will not change, but optical path will change. In the last mock exam, you have a question over the optical path measurement. Many of you write A plus AB, A and B by root 3, and that is wrong. 2A plus 2B is the correct answer. There is a question related to the optical path, because whenever the light travels in the denser medium, if geometrical path is B, the optical path is not B. It will be mu times B. It will increase because light goes slowly. So as a result, the distance will actually increase. So the same thing happens. Now central bright will not be formed at O, because previously when there will be no slab in the path of the light wave 1, then S1O and S2O, these two distances are equal. Now, since we introduce the slab in the path of wave 1, then optical path of wave 1, which reaches the point O, will change. As a result, S1O optical path and S2O, these two are not same now. Okay. Now, as soon as they are changed, the central bright will not be formed at O. It will be formed at any other point. So suppose central bright forms now at this point, O prime. Then there is a change in the central bright fringe. So that change is called the shift of the central bright. Let us consider it as delta x. Now if you can measure delta x, then you can measure the T, that is the thickness, because we can find a relationship between T and delta x. But the problem is that if you are taking monochromatic light, then suppose 50 fringes are produced. Among them, one is central bright. All the fringe system shifts. You cannot look at what is your central bright right now, because all are equally intense, equal width and same color. Because in interference we proved that all fringes are of equal width and all fringes are of equal intensity. As a result, all the entire thing is shifted. Now how to find which one is your central bright? All fringe look same, so you cannot find it. What is your central bright fringe right now? So the shift we cannot measure, and as a result we cannot measure the thickness. The only way to measure the thickness is to use interference by white light. The S point source to be taken as a white light source. Now what is the advantage in that? In case of interference by white light, only the central bright will be white colored fringe. Okay. And there will be no dark fringe. All other are colored fringes. Because suppose at any position there is a third order dark for yellow. Okay, third order dark for yellow. But in that position, second order bright for green will fall. As a result, you cannot see that position as dark, rather you will see that position to be green. So in this way, all such positions of the dark fringes will be changed because of the overlapping of the other order bright fringes of the other colors. So no color's dark fringe is visible in the shape. Suppose for second order dark of blue should be somewhere, or in that position suppose fifth order red will fall. So you cannot see the dark for the second order blue, you will see it red. So only central fringe is white, remaining all other fringes are colored. Okay. So first you can see here a white colored fringe. Suppose this dark is considered as white. Then suppose red colored fringe, two red colored fringe on both sides. Then suppose yellow colored fringe on both sides. Then suppose green colored fringe on both sides. Then blue colored fringe on both sides. And again this order repeats. Means this is first order red, that is second order red, third order red, fourth order red, and all colors are white colors, they are formed like this. Now if you introduce the slab in path of this, entire fringe system will shift, but you can easily identify where is the new position of the central bright, because only one fringe is white, rest of the fringes are colored. So you can easily find the new position of the central bright and calculate the shift of the central bright fringe. But in a monochromatic light, it is not possible for us to find the shift of the central bright fringe. So only for this experiment, interference in white light is used. And if how many dark fringes are produced in interference experiment with white light? The answer will be no dark fringes are produced. Okay, because sometimes this type of question asks that 4 dark fringes are produced, 10 dark fringes are produced, no dark fringes are produced. So the answer will be no dark fringes are produced if the interference is performed with white light. Only you will see the color fringes. Another thing is that how to measure the thickness of this slab. That part is a part of JEE. Thickness of the slab calculation is not in the next syllabus. So only the property of the white light interference you have to know. The remaining part, how to calculate the thickness of the slab and all these things, that is not required. Okay. Now, in the interference, bright and dark alternate pattern will be formed. That means in the position of the bright fringe, more energy will be produced, and in the position of the dark fringe, energy will be absorbed. But does it imply a violation of conservation of energy? Because at the position of the dark fringe, energy is destroyed, you can consider, and at the position of the bright fringe, energy is produced, you can consider. So does it a violation of conservation of energy? Conservation of energy is a fundamental principle which cannot be violated. Okay. The overall intensity or the average intensity in the interference pattern will remain same. If there is no interference, still remains same. Because the energy that is disappeared from the position of the dark fringe will actually reappear in the position of the bright fringe. So there is a redistribution of energy or redistribution of intensity. There is no loss or gain in energy or intensity. Total intensity remains same. So interference experiment is consistent with conservation of energy. Okay. So if slit 1 is open, you can consider that light is coming through this and intensity of the light should be I1. If slit 2 is only open, then you can consider light is coming through this and intensity will be I2. So intensity or energy is a scalar quantity. So we can consider that if both the slits are open, the total energy should come to be I1 plus I2. But in the interference you got that term I1 I2 plus 2 root I1 I2 cos delta. Now if you are taking the average value, I average, by calculating this integral 0 to 2 pi I d delta by integral 0 to 2 pi d delta. This is called the average intensity. This will come out to be exactly I1 plus I2. Means there is no change in any part of the total intensity. Now how I claim this one? Because the formula for I that we have already derived, that is I equal to I1 plus I2 plus 2 root I1 I2 cos delta. Okay. Now if you put that I here, first term is I1, so that is taken common. So integral d delta by integral d delta, that will cancel. For second term I2, same thing will happen. For last term 2 root I1 I2 taken common, it will be integral cos delta d delta. What is the integration of cos delta? Sin delta. Limit is from 0 to 2 pi. Means sin 2 pi minus sin 0. Sin 2 pi is 0, sin 0 is also 0. So 0 minus 0, 0. So last term cancel. And you will get only I1 plus I2. So total intensity remains, average intensity remains same. I1 plus I2. There will be no change in average intensity. If there is a change in average intensity, then we can consider that energy conservation is violated. Okay. Now, one more thing related to the interference, that is, suppose we are considering the interference of monochromatic light. Okay. Now, the first wave, interfering wave's amplitude is considered as 50. Intensity of the first interfering waves is considered as 50. Unit. Some unit is there. Unit I haven't tried. 50. More than. For second one, intensity is 2 unit. First one, amplitude will be, amplitude of the first interfering wave is 50 unit. Amplitude of the second interfering wave is 2 unit. And in the second case, amplitude of the first one is taken 50 unit. Amplitude of the second one is taken 47 unit. Okay. Which pair will give you better interference pattern? Which pair will give you better interference pattern? Means contrast of the interference pattern is very good. In which pair? Suppose this kind of 4 options are given and you have to find out the correct option for which contrast of the interference pattern is very good. Suppose you have given a task that you have to paint this whiteboard. Okay. First one of you uses different shades of yellow color to paint this whiteboard. Okay. Different. Some is very vibrant white, some is very shabby, some is a little bit faint like this. You paint this different part of the whiteboard by stroke. Another whiteboard is there, identical, and some other student of you are saying that complete this painting. She or he uses different colors. Suppose yellow, then red, then green, and then blue, like this. Which board appears more vibrant? First one or second one? Second one. Even if the second student paint it by one black stroke, then some gap left for white portion, then another black, another black. But between every black there is a white one. Still, second one uses a single color, but his contrast will be more. Since first one uses different colors of shades of yellow, the contrast is not that much. Okay, why? Because the second student uses dark. For the dark he uses yellow, and for the bright he uses white. So the intensity for the dark region is almost 0, and intensity for the bright will be very high. so the contrast will be very high. As a result, you can easily visualize this pattern, which one is dark and which one is bright. First one uses different shades of yellow which are almost of equal intensity, almost. Suppose one is almost of equal intensity, so whenever they are painted, the bright portion is yellow, dark portion is some shabby yellow. So difference between bright and dark intensity is not that much. That's why it loses contrast. Okay. So contrast high means intensity will differ too much. Then only contrast will be high. A dark color and the same color's shabby faint color will not give you better contrast. Okay. So contrast will be better only when the intensity will be differ too much. Now how it comes? See, the expression for I 2 A1 A2 cos delta. Now what is the maximum intensity? What will be the value of cos delta for maximum intensity? Plus 1. So it will immediately become A1 plus A2 whole square. And for minimum intensity, A1 minus A2 whole square. Now check. If you consider the first pair, A1 is 50, A2 is what? 2. So in that case, I max will become 52 square and I minimum will become 48 square. Okay. And if you consider the second pair, then I max will be and I minimum will be. So in which case you can see the difference between bright and dark clearly. Second pair. Because bright is 97 square, is very bright, very intense, and dark is 3 square, means very less intense. But in the first pair, bright is 52 square, dark fringe is 47 square. So 52 square and 47 square has not that much of difference in intensity. But 97 square and 3 square are too much different in intensity. So that's why in this case the contrast will be very high and you can clearly visualize which one is bright and which one is dark. And here the visualization of the bright and dark, it is difficult to determine bright and dark for a longer period of time because your eyesight will be used after some time. It will be fatigued after some time and it cannot distinguish between two almost close intense colors. Okay, so for better intensity, the intensity of the colors should differ too much such that the contrast will be high and we can visualize the pattern properly. So it is a basic criteria of the sustained interference pattern that amplitude of the interfering waves should be very close to each other such that dark fringes will be almost dark, bright fringes will be too intense. Okay. So for the better interference, A1 should be almost equal to A2. If it is equal, then exactly, then it is a hypothetical, it is an ideal case. A1 equal to exactly A2. But even if they are not equal, they should be very close to each other. Okay. Now write down another question. The ratio of maximum to minimum intensity. The ratio of maximum to minimum intensity in a Young's double slit experiment with monochromatic light. In a Young's double slit experiment with monochromatic light is 25:1. 25:1. Find the ratio of the amplitudes of the interfering waves. Find the ratio of the amplitudes of the interfering waves. 4. In a Young's double slit experiment with monochromatic light, the intensity of the ratio, maximum and minimum intensity ratio, maximum and minimum intensity ratio is 25:1. Then find the ratio of the amplitudes of the interfering waves. Intensity maximum to intensity minimum. This ratio is given. You have to find the ratio of A1 and A2. See, these two are given. I max by I min ratio. That is given 25/1. Then A1 plus A2 square by A1 minus A2 square. You have to find the ratio of A1 and A2. Use this formula. A1 plus A2 square by A1 minus A2 square, that is equal to I max by I min. Okay, that's from that formula. Then we can write here A1 square, A1 by A2 square by A1 minus A2 square, A1 plus A2 square by A1 minus A2 square. That is 25/1. Then calculate A1 by A2. 3/2. So A1 by A2 is coming 3 by 2. Take a square root on both sides and then calculate A1 by A2. Okay. Now, there are two more parts of the wave optics. One is diffraction of light, another is polarization of light. But before doing that diffraction and polarization, read once this interference topic from any book or NCERT that you have, or any other book that you have. From that, first read this one, then I will discuss diffraction and polarization, the remaining effect. Because once you have a good knowledge of interference, then you can understand the diffraction properly. Now, I will discuss in 45 minutes is available, so I will discuss any small topic from the modern physics portion because that is very easy. Earlier we have discussed the digital electronics part. Previously, digital electronics part we have discussed, but not the other parts. Analog electronics part haven't discussed. So analog electronics part is very small because transistor is not there, so we can manage almost entire part within 45 minutes. See. So first read, there will be a study session at night. So in that study session, from any book, any source you have, NCERT or any other. So read this interference topic through. Then in tomorrow's session morning, we will discuss the diffraction. First we will consider the semiconductor. What is a semiconductor? And what is the need of the semiconductor? See, we know that basically there are three types of materials. One is conductor, another is semiconductor, another type of material is insulator. These are categorized based on the ability to carry electric current. So on the basis of electric current flowing capacity, the materials are divided into three parts: conductor, semiconductor and insulator. Now, what happens to this semiconductor, conductor and insulator means what happens to the materials such that some materials are carrying electricity easily, through some other materials electricity cannot flow easily. That can be explained on the basis of the energy band diagram. Energy band diagram. Now, we know that if we consider the Bohr atomic model, in the central part of the atom there is a nucleus, and outside this nucleus there are different orbits in which the electrons are revolving around the nucleus. The outermost orbit, okay, so that is far away from the nucleus. So on that electron which resides in the outermost orbit, the nucleus has very small attraction on them, because attractive force is almost Coulomb force, and Coulomb force decreases with distance because it is an inverse square force. So outermost orbit electrons are very loosely bound with the nucleus. This outermost band in an atom is called the conduction band. Outermost electron band is called conduction band. Write down. outermost electron band is called, in an atom, is called conduction band. Okay, and the electrons in this band are loosely bound to their parent nucleus. And the electrons in this band are loosely bound with their parent nucleus because the distance is too large. As a result, attraction force of the nucleus will be very small. Now, as a result, these electrons can freely roam inside the material. It cannot leave the material surface, but it can roam inside the material. Means one atom to another atom it can move, but it cannot leave out of the metal surface. Okay. These electrons can roam freely inside the material. These are called conduction electrons. These are called conduction electrons. Okay. Because whenever you apply some voltage, these conduction electrons freely move throughout the material and they conduct electricity. Clear? Now, just below this conduction band, another band, electron band, is there, which is termed as valence band. Just below this conduction band, another electron band exists, which is termed as valence band. Right now, just below the conduction band, another electron band is present, which is called valence band. Okay, this valence electron cannot freely move through the material. Cannot freely move through the material means this valence electron cannot go from one atom to another atom. Cannot roam freely through the material. They can only take part in chemical reaction. They can only take part in chemical reaction. Okay, chemical reaction is occurred because of the exchange of the valence band electrons. Okay, now of course valence band electrons are more strongly bound with the nucleus because that is closer to the nucleus. This is valence band, this is conduction band. This is conduction band. This one is valence band. Conduction band. Okay. Now, First one, insulator, semiconductor. Conductor. Means in case of a valence insulator, the energy gap between valence band and conduction band, this gap is called the energy gap, because from Bohr atom model you know that for each electron band there is a definite value of the energy. Energy is quantized. For hydrogen atom you know it is minus 13.6 by n square electron volt, and it varies with n. So different values of n will imply different values of the energy. Now for insulators, valence band and conduction band's energy levels gap is too large. For semiconductor, that is moderate, and in case of a conductor, that gap is almost very small, negligible. Means even you cannot separate the bottom portion of the conduction band to the top portion of the valence band. These bands are almost overlapped. Okay. Now what happens when you supply external voltage? Then already in the conduction band of the conductor, too much electron is present. Additionally, valence band electron can also behave like conduction band electron, because band gap is very small and bands are overlapped. So valence electron, conduction electron both behave like conduction electron. So there are enormous number of free electrons available in the conduction band. So that's why these materials are behaving like conductors. Mostly in case of metals, this phenomena occurs. That's why almost all metals are good conductor. Okay. All metals are almost good conductors, because in that case valence band and conduction band almost overlap. So not only conduction electron can take part in the current electric current flowing, even the valence electron will come to the conduction band and they will behave like conduction electrons. Fine. Now, in case of semiconductor, the gap is small. Means if you supply sufficient amount of voltage, then some of the valence band electron can be promoted to the conduction band. Okay. Then electricity will can flow through these materials. These are called semiconductors. Means at the normal temperature, valence electron cannot go to the conduction band like conducting materials, because for conductor in the normal temperature, this valence electron go to the conduction band. Okay, but in that case, normally valence electron will not go to the conduction band. You have to apply external voltage sufficient amount such that the valence electron are promoted to the conduction band. Then in the conduction band, some good number of electrons are available such that this material can conduct electricity. That's why it is called semiconductor. And in case of insulator, this gap is too large such that even if you apply sufficient amount of large voltage, it is very difficult to transfer the valence band electron to the conduction band. Okay, so that's why these materials cannot conduct electricity and called insulators. Okay. Now, first of all, conductors are usually such conduction band electrons are too large in the conductor, so they are best material for the flow of electricity. No doubt about it. Then for the semiconductors, we have to promote the valence band electron to the conduction band. Then only it will allow through this it will allow the flow of current. Then why semiconductors are used in some cases? Can't we use conductor in all cases? Semiconductor requires some additional bias, additional voltage, such that some valence electron go to their conduction band. But in case of conductor, this additional voltage is not required, so it is already in the conduction band. So it is the best conductor, but still we are going for the second best in some cases. So can't we prepare all the devices by using conductor? Why semiconductor is required in some cases?
So like standard resistors.
Yes?
Standard resistors.
In case of
Standard resistors.
standard resistors, which resistors is prepared by semiconductor? All the resistors are conductor. The resistance that is given to you in the experimental lab, they are not semiconductor. What is the need of semiconductor? Don't say any semiconductor device that this preparation of this device requires semiconductor. I am asking for which purpose? Our purpose is to flow the electricity through the material. That is our main purpose. And we know that that purpose can be exactly solved by conductor. Then why semiconductor?
Conductor resistance increases.
That is another property. But initially you have to supply voltage. See, in some cases we require certain kind of a material in which, suppose we are taking a conductor and we connect it with a battery. This resistance means some conductor, suppose copper conductor. Okay, resistance R. This I. Now, if I change the polarity of the battery, in which direction current flows? In opposite direction. So if I change the polarity, suppose same battery, but I change the polarity, so current will flow in this direction. Okay. But some circuits are required in which we prefer that current should flow in only one direction. And when the polarity is reversed, the circuit will stop the current flow. That means it behaves like a valve. So for that, semiconductor has to be used. Conductor cannot be used as a valve because it will allow the flow of current in both ways if the polarity of the battery is reversed. But in case of semiconductor, in one direction it will allow current to pass through. If you change the polarity of the battery, it will become reverse bias and it will not allow current to flow. So due to this, semiconductor devices are used. This is the primary object of the semiconductor. Okay. Now, there are two types of semiconductors. Mainly, one is called the intrinsic semiconductor, another is called the extrinsic semiconductor. Mainly, as a semiconductor materials, we use silicon and germanium. These two are widely used as the semiconductor material. Silicon, germanium. Both have the valency 4. Okay. Now, intrinsic and extrinsic means, what do we mean by intrinsic and extrinsic semiconductor? See, suppose we are considering a silicon crystal. Since their valency is 4, I can consider like this. I will consider complete block. Now consider the central atom of the silicon. Okay. This central atom of the silicon is actually preparing 4 covalent bonds because it has valency 4. It produces 4 covalent bonds with the 4 nearby silicon atoms. See, this one. See, this one, and this one, marked by red. Okay. This particular silicon atom is making covalent bond with the 4 nearby silicon atoms by sharing electrons. So, since they are sharing electrons, that's why 2 lines are drawn to denote that it's a covalent bond. Okay. Now, if you so this structure is repeated because there are enormous number, million trillion of silicon atoms in a chunk. Now, around this chunk, if you apply external voltage source, okay, what will happen? This voltage source, positive terminal of the voltage source will attract the electrons and negative terminal of the voltage source will repel the electrons. As a result, this covalent bond will break and electrons will come out from the covalent bond. So since external voltage is applied, this covalent bond breaking the electrons that are coming from the rupturing of the covalent bond has sufficient kinetic energy, and these electrons will straight away go to the conduction band and behave like conduction electrons, and as a result this material will conduct electricity. But there is another thing is found by an experiment called Hall effect. There is an experiment called Hall effect. It is found that only one kind of carrier of electricity is not there inside this semiconductor. There is another kind of carrier of electricity, not only the electrons. That is hole. Because while the electron will, so initially this covalent bond, this is neutral. So when the bond is ruptured, electron is coming out, means this portion of the bond will become positively charged. So on the removal of the electron, the remaining part of the bond is positively charged. So this positive charge which stays in the broken covalent bond is called hole. Okay. So electrons, due to its kinetic energy, will easily go to the conduction band, but this hole cannot go to the conduction band. Hole will stay within the valence band. So two currents are moving inside this semiconductor. One is due to the movement of electron, another is due to the movement of hole. So the movement of electron occurs in conduction band, whereas movement of hole occurs in valence band. So through the valence band, Due to the movement of hole, a current will be generated. Through the conduction band, due to the movement of electron, a current will be generated. So total current will be sum of these two, because both current will flow in same direction. Why? Because if the electric field is there along this, the electron will move in the direction opposite to the field. Electron will move in the direction opposite to the field, because electron feels the force opposite to the direction of the field. Then electron moves here. So in which direction current flows? This is electron current, I consider. Okay. And hole is a positively charged particle. So in which direction it will feel force in this electric field? And the current for the positive charge is along the charge, movement of the charge. So this is the whole current, IH. So electron moves in opposite direction, so electron current is opposite to the flow of the direction of electron. And hole is a positively charged, so its direction and its current direction are same. Electron negatively charged, so the movement of the electron and direction of current for the electron is opposite. Okay. Since in the semiconductor both the currents are in same direction, so total current I will be equal to IE plus IH. This is the total current in a semiconductor, intrinsic semiconductor. Okay. And both current contributes to the same amount. Both current contributes to the same amount, because charge of a hole and charge of electron are same. So charge per unit time is also same. Charge per unit time is also same. So both the currents will be same. Now why? Because as you increase the external voltage, the covalent bonds will be ruptured. But on rupturing each covalent bond, one electron and one hole will be produced. So number of electrons and number of hole produced will be always equal. As a result, IH and IAE both are equal in magnitude, but there is a significant difference. That is, IP will produce more heating effect. IH means hole current will produce more heating effect than the electron current. Both current are same in magnitude, but IH will produce more heating effect. Why? Hole passes through valence band. Electron passes through conduction band. You remember one term in current electricity we discussed, that is called the mobility. Drift velocity per unit electric field. Mobility. So mobility of the electron is more than the mobility of the hole. Mobility is similar to friction. So hole suffers more friction. As a result, they will produce more heating effect. Electron suffers less friction. When electron passes through the conduction band, and conduction band is far away from the nucleus, hole passes through the valence band. Valence band is close to nucleus. As a result, and there is a slight difference between the mass of the electron and hole. So hole will suffer less mobility. Mobility less means it will suffer more friction. And electron has more mobility, means electron is very swift in flowing. So that's why current will produce more heating effect than the electron current. Now, this type of semiconductor, though very good, but are of no use. Why? Because this cannot be used as a valve. Because our main aim is to use the semiconductor as a valve, but this cannot be used as a valve, because if you give a polarity in a particular direction, so electron will be there, hole will be there, both charges will be there. So for one, if it is forward bias, then for the other one it will be reverse bias, and their magnitude of the charges are same. So same current will flow in each cases. As a result, this cannot be used as a valve. So we have to use extrinsic semiconductor. Extrinsic means you have to put some impurity while preparing this semiconductor material. You have to put some impurity. Now, how impurities can be used? Means entire silicon is in a liquid state. Suppose in the liquid state, if you put it to be condensed, then it will slowly form the structure, crystal structure. While it is forming the crystal structure, it is in the liquid state. It is about to condense, not yet condensed. At that moment, you put some impurity atom everywhere. As a result, these silicon atoms will be clustered around that impurity atoms to form a crystal structure. Previously, silicon atoms are clustered around the silicon atoms. Now around that impurity atom, every electron, every silicon atom will be clustered. This is the phenomena like that. All of you are the people of Meghalaya. Now, suppose another Meghalayan people, Meghalayan, suppose any doctor visited this place, and what you will do? He is a famous doctor of any reputed hospitals of Meghalaya. He visited this place. What you will do? You will eager to hear him, what he will say. But suppose Virat Kohli visited this place. What you will do? You will gather around Virat Kohli for an autograph. The same thing silicon atom will do. Normally they are structured like this. Now as soon as you will put the impurity atom, impurity atoms are like Virat Kohli, all the silicon atoms try to gather around it. And suppose there are 10 Virat Kohli in this room. So all of you, if there is one Virat Kohli, all of you are not getting that chance to go to the Virat Kohlis in front of Virat Kohli. So if 10 Virat Kohlis are placed one by one, so there is a local cluster, there is another local cluster, another local cluster. So this type of cluster will be formed. Now, I will change this by considering this one as a different atom, and these silicon atoms are clustered around that different atom, and this structure is now limited. Initially, two types of impurities can be added. One is a pentavalent materials impurity, suppose phosphorus. Another we can do by using a trivalent, suppose arsenic. Okay, so first we consider of using phosphorus. So these are silicons. This is phosphorus. So what will happen? 4 covalent bonds will be formed. But remember, silicon have how many electrons? 4. Silicon, valence electron 4. Phosphorus, valence electron 5. So phosphorus will donate 1 electron. This silicon will donate 1 electron to produce covalent bond. Similarly, this silicon donate 1, this silicon donate 1, this silicon donate 1, this phosphorus donate 1, this silicon donate 1, phosphorus donate 1. Okay, fine. but there is still one electron left in phosphorus. Okay, that cannot form the pair. Extra electron. That is called a lone pair electron. And lone pair electrons are very loosely bound with the nucleus, because nucleus has very low attraction on a lone pair electron. Okay. This is that lone pair electron. Very loosely bound. Now, since it is loosely bound, it can be easily detached. Since it is very loosely bound, it can be very easily detached. And as a result, when you apply the external field, this electron immediately goes to the conduction band for producing for the flow of electricity. Okay, so this type of semiconductor in which electron is the majority carrier. See, before any rupturing of the bond, electron is present in the conduction band. Okay, now even if the bond ruptures due to potential, equal amount of electron and hole will be produced further, but initially the number of electrons is raised. That difference cannot be changed. So the electron is the majority carrier in this case, and this is called N-type semiconductor. N-type. N-type means majority carrier is electron. Okay. Now, if you use trivalent, then arsenic require one more electron. So this is called a P-type semiconductor, because there is a formation of hole, because it cannot produce a covalent bond. There is a lack of hole, there is a lack of electron for producing a covalent bond. So that is considered as lack of electron is considered as hole. So that hole will stay in the conduction band. Don't say that if we apply the external voltage, hole will go to the conduction. No, this hole will stay in the valence band for producing current. So even now when P-type conductor is there, hole is the majority carrier. Now you apply voltage, this hole will move through the valence band to constitute current. So two types of semiconductor we can prepare by extrinsic method. One is P-type, where electrons are majority carrier, and where one is N-type, where electrons are the majority carrier. One is P-type, where holes are the majority carrier. Clear? Now we have to take PN junction. Now say how to prepare the PN junction. I will prepare a P-type, I will prepare a N-type and attach it by gum. Very good. So how can it be prepared? If it is not attached with Fevikwik or Fevicol, then how can it be prepared? One is P-type, another is N-type. Then how to consider a PN junction? Create a PN junction. See, entire silicon chunk, liquid state. In this material, entire liquid taken in a container. In one side, drop some phosphorus. In other side, drop some arsenic. Automatically, in a single crystal, one side will be P-type semiconductor, another side will be N-type semiconductor. In a single crystal, in a liquid state, you have to drop, such that when the crystal growth occurs, one side will be P-type, one side will be N-type in a same crystal, not two different crystals and then add these two. In this way, it cannot be prepared. Single crystal, you have to prepare this. Okay. Now, So suppose this side is P side, we consider this side as the N side. Clear? Now what happens? That we will discuss in the next class, because there are many cases of the depletion region and all these things that we have to discuss. Barrier potential. And remember, this portion is very easy. The questions of these portions are also very easy. So try to do it very fast, because modern physics, entire modern physics questions are very easy. It is not like that of electrostatics or mechanics that you will face too much problem in calculation.